Hello guys, welcome to Bugs in Code, and the problem that we are going to solve today is number of good components. But before that, if you're new here and a person who likes stuff related to coding, then you can subscribe my channel so that you never miss out an update. So let's get started. This is the problem statement, and it says that given an undirected graph with v vertices numbered from 1 to v, so it's basically following one based indexing, and e edges. Find the number of good components in the graph. But what's a good component? So a component of a graph is good if and only if it is a fully connected component. Okay. And what's a fully connected component? So a fully connected component is a subgraph of a given graph such that there's an edge between every pair of vertices in a component. Given graph can be a disconnected graph, sure. And consider adjacency list from index 1. Okay. Now let me explain this problem. So I'm going to take an example. So let me take an example here. An example is going to be 1, 2, and 3, 4. After that I will have 5, 6, 7, and I will have 8 and 9. Okay, so for this graph we are going to check how many connected components are there. So how many good components are there? So is this a good component? Let's check. From this 5 we can go to 6 and we can go to 7. Okay, from this 7 we can go to 5 and we can go to 6. Now similarly from this 6 we can go to 5 and we can go to 7. So it's a good component, yes. So I will have my counter as 1. So this is basically my answer. Now if I check for this component, from this 8 I can go to 9, and from this 9 I can go to 8. So I'm going to increase my count as 2. So my count is going to be 2 now. Now after that I will check for this component. So it's single, it's containing a single like node. So from this 2 I can go to 2. So this is my counter is now going to be increased to 3. Now this is not 2, it's 3. After that I will check this component, like I will check this one. So is this a fully connected component? Let's check. From this 1 I can go to 3, and from this 1 I can go to 4. Nice. From this 4 I can go to 1, but from this 4 I cannot go to this 3, and that's where we face a problem. So it is not going to be a fully connected component. It may be a fully connected component in case when it will surely be a fully connected component when we have this one edge. But right now it's not a fully connected, so my output is going to be 3. I have 3 fully connected components like this one, and this one. Okay, I hope you guys got the clear understanding what the problem actually says, and let me just move to the solution now. Okay, so let me, before moving on to the solution, I would like to explain you a very important concept, which is detecting a fully connected component. Once you understand this concept, you will surely be able to solve this problem. So this is something which is a very important concept, and it is going to be used in various other problems as well. And one more thing, if you know this concept or if you understand this concept, then you can use either BFS or DFS to solve this problem. Doesn't matter which one you choose. So let me start. Let's get started. I have an example 1, 3, and 4, and these all are connected. Now let me ask from you, it is a fully connected component or not? If you see this, yes, from this one I can go to 3, from this one I can go to 4. Similarly from this 4 I can go to this one, and I can go to this 3 as well. It is a bi-connected edge, so I can go to it is a bi-directional edge actually. So from this 4 I can go to 1, and from this one I can go to 4, no doubt, undirected graph. Now similarly from this 3 I can go to 1, and I can go to 1, 4. So yes, it is a fully connected components, but how to write a program, to how to tell a computer to detect this? What one observation that I'm going to make here is observation. One observation that I can make is if I have n edges, n nodes. So if I have n nodes, it is basically a nodes count. So total number of edges that I should have in a fully connected components is n into n minus 1 by 2. How I am saying that? Let me tell you mathematically. So if I have one edge, two edge and three edge, I'm explaining for three. So 1, 2, 3. Now uh, okay, so let's take more edges like more nodes like 1, 4 and up to L. I have various and n. So there are so many nodes. Now this one, if there are n nodes, so each of the node will be connected to n minus 1 other nodes. Is there any doubt in this? No, I don't think there should be any doubt. Like for this one will be connected to all other nodes except this one. So and similarly there are n nodes. So n nodes will be connected to n minus 1 other nodes in a fully connected graph. So that's why we are saying that total number of edges must be n into n minus 1 by 2 in a fully connected component. And if I validate this, so let me take an example like for n is equal to 4, 1, 2, 3, 4. One more example is there. For n is equal to 4, I should have edges as 4 into 3 by 2. So it is basically going to be 6. And 4 I already have. I'm going to have one more and one more. So these are total 6 edges. And yes, it is a fully connected component. Now let's move on. Let's move to the solution now. I hope you guys got the clear understanding how to detect a fully connected component. So what I'm actually going to do is I'm going to loop all vertices, and if not visited, if not visited, like current vertex is not visited, then I'm going to do a traversal. So one more thing I should tell you that this question now becomes a simple problem of traversing the whole graph. So once I traverse, I'm going to count the nodes and edges. So I will have a value of n and e, and I'm just going to check fully connected components by the formula that I have explained above, like by this formula, So now let me explain this. Let me move to this part again, and here I will use BFS or DFS, basically the traversal. So I will basically do the traversal to and check what the particular condition, like n should be equal to, like e should be equal to n into n minus 1 by 2 in order to check fully connected components. So if this condition is true, I am going to increase my answer variable by 1. Like yes, we have found one fully connected components. Now let me just explain you why I am checking. You may ask a question from me like, hey, why are you checking this particular condition? So let me explain why I'm checking this condition. If I have a graph like 1, 2, 3 and 4 and like this, and I have checked for this one when I was at 1, then I came to know that yes, it is a fully connected component, so I have increased my answer as 1. Now when I come to this 2, so I will check the same thing again and I will get another true, then it will become 2, and similarly this will become for this it will become 3, and it will become 4 for this. Now was there 4 fully connected components? Obviously not. So what we are going to do is, once I have checked the fully connected component associated with this one, then I am going to mark them as true, 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 which means don't check for these nodes. So we are not going to check these nodes, or we can say we are going to avoid these nodes. So that's what we are doing here. Now I hope you guys got the clear understanding, and let me just now move to the solution part of this problem. So this is the problem on Geeks for Geeks, and I'm even going to provide the link in the description box. So what I'm going to do is just loop all the vertices, and since it is following one based indexing, so I'm starting with one and ending at the last. And I will check if my current vertex is visited or not. So if it is visited, then I'm going to continue. I'm just going to avoid this vertex, and I must have one array which is visited because we are using it somewhere in a program. So v plus 1. Why v plus 1? Because one based indexing again, and answer is going to be initialized with 0. Now let me do a BFS traversal in order to check, and it is going to return a boolean value. So I'm going to check if this is true, then I'm going to increase my answer, and at last I'm going to return my answer. Simple. Now this BFS function is going to take first of all the current node and graph and visited, and uh, and that's all. Now public boolean, so this function is going to boolean, and I will say BFS. Now I will start with my current vertex, and I will have a graph adjacent, and I'm going to have a boolean visited, and I'm going to have one more thing. Okay, so this is all. Now in order to start a BFS traversal, I need something which is a queue data structure. I hope you guys know this thing, and I'm going to add the current vertex in my queue. Now while my queue is not empty, I'm going to do something. What I'm going to do is, okay, one thing, as I explained you in the con while explaining the solution, so I will have a node count which is be nodes, isn't it? And it will be currently 1, and after that I will have an edges count, so I will call it degree, which is going to be okay. So how to count edges? Like currently it is going to be, let me explain here. So how to count edges, like how to count edges, let me tell you here. So if I have an adjacency list, like from this one I have connected 2, 3 and 4. From this 2 I'm connected with 3, 4 and 1. For this 3 I'm connected with 2, 4 and 1. So like this, if I have something, so for this one, how many edges are there, outgoing edges are there from this one? Obviously 3, because from this 3, adjacency list is something which is showing how many connected edges are there. So similarly for this 2, I have 2 edges, but there is something which I say a repetition. So like one, if I have an edge like this, so first of all I'm counting this 2 for this one, and I'm connecting this one for this 2, so I will get count as 2, but there is only one edge. So at last I'm going to divide my degree by 2, like whatever the degree of our graph is, I'm going to divide it by 2. So now let me just move back to my code part, and what I'm going to do is I'm going to get my adjacent dot get current vertex size. I'm going to initialize my degree with this, and now I'm going to even I'm going to visit it here as well. So it is visited now, and let me just retrieve the value of q from here. So value is going to be my you can call it value, or you can call it the current vertex, so I'm going to call it current. So for I'm now traversing the neighbors, so adjacent dot get current, and now I will check if my current is visited or not. So if it is not visited, then I'm going to visit it first of all. So now it is visited, and I'm going to add the queue. Now two very important operation. The first is my nodes count is going to be increased by 1 because I have found one unvisited vertex, and my degree count is going to be adjacent dot get in dot size. I mean all the neighbors, because each neighbor is associated with one, like each neighbor is actually associated with one edge. So now I'm going to return degree by 2. Why degree by 2? I have already explained you. So degree by 2 is equal to nodes cross nodes minus 1 by 2. So this was the condition which we should check. Now this is all for the solution. Let me check whether it works or not. Let's see, it may show compilation errors. Okay. Okay, so it's working for the example test case, and let me just submit this now. I hope it will work. Let's see. Okay, so it's working, and this is all for the problem. Now let me explain one more approach, because since we are clear with the concept, so we just need to change the function here. So instead of this BFS, I would like to call it a DFS. Here also I will call DFS, and now what I will do here is I will have an array. Like I have to denote the nodes. I have to get the node count and the degree count. So in okay, so what I'm going to do is make them array, because I'm going to, since DFS is something which is implemented with the help of recursion. So I'm going to make a reference variable, which will be nodes will be initially 1 and degree will initially be my adjacent dot get current node dot size. Okay, now I'm going to call a what we say is a recursive function, which is dfs util, and from the first vertex adjacent visited, and I will have nodes and degree. Okay, at the end I am going to check the same condition if my return degree of 0 by 2 is double equal to nodes of actually this is an array, so that's why I'm writing nodes and degree here. So nodes of 0 cross multiplied by nodes of 0 minus 1 by 2. Now I have a function which is the actual DFS recursive call, so it's going to be a type void, and I will have DFS util. So I will have a source vertex and graph here adjacent, and I will have a boolean visited array. After that I will also have nodes count, and I will have something which is degree. Now what I can do is, first of all I will visit the current vertex. Okay, so even similar to the BFS, I'm going to visit it here, and what I'm going to do is I'm going to start traversing the neighbors directly, and it is going to be adjacent dot get I, like current neighbors, and if it is not visited, then I'm going to visit it. So visited in is going to be true, and I'm going to call for the current, but before that I'm going to increase my nodes count and my degree count as well. So degree is going to be adjacent dot get in dot size. Now I'm going to call my function for the current vertex, which is in and adjacent, and I will have a visited nodes and degree. Okay, so this is all, and let me just check whether it works or not. Is there any compilation error? No. So okay, it's working for the example test case, and let me just submit this solution. Okay, so it is also working, and this is all about this problem. I hope you guys like the solution. So if I summarize it, so one and only important thing in order to solve this problem is to detect how to find whether, how to check whether component is connected or not. So that's what we do with this particular formula, which is n cross n minus 1 by 2. And this is all for the now. Thank you.